Welcome to my lesson on circles. So as in previous lessons, I will first just go over some theory and then go over some past paper questions using the theory that I have just discussed. And I'd just like to mention that with circles, there's not much external knowledge that you need. It's mostly just what you learn in GCSE, so circle theorems. But the trick is to try and apply them in a unique way that allows you to solve the question. Okay, so the first theorem that I would like to talk about is that the angle at the center of a circle is twice the angle at the circumference of a circle. So what does that mean? Well, if we have a diagram as such, and this point here that I have marked with an X is the center of the circle, then what it means is that B is equal to twice A, 2A. So this angle B here is twice the size of angle A. And one way that I like to think about it is if I draw a line like that, you can see then we have created two triangles. One bigger one with a vertex, all vertices are on the circumference of the circle, and a smaller one where two vertices are at the circumference and one is at the center of the circle. And if you can connect two vertices as such, then you can apply this theorem. And so just for the sake of it, I will write it here. So we have B is equal to A. Okay, so now I'm just going to quickly show a proof of this theorem. So the first thing to do is to connect the center here to this point here on the circle. So I'll just quickly join it. Okay, so this now gives us two triangles and we can start labeling the angles. But before I label the angles, I just want you to appreciate that both of these triangles are isosceles. Why are they isosceles? Well, if this is the center of the circle and we're joining the center to the circumference, then clearly this side here, and this side here are all radii of the circle. And since the radius of a circle is constant, these three sides are of the same length. Okay, so knowing that, I'm now going to label the angles in both of the triangles x, y, and z. This angle here, we'll call it Z. This one here, W. And we can call this one here Y. This one here is also Y. And then this one here will be X. And this one here will also be X. Okay, so because angles in a triangle add up to 180, we can say that 2x plus z is equal to 180. We can also do the same for the other triangle and we'll get 2y plus w is equal to 180. So this equation here, that'll give us z is equal to 180 minus 2x, and this one will become w is equal to 180 minus 2y. Now, if we call this angle here, so this one here, if we call that, call it B for now, because angles around a point add up to 360, B plus 180 minus 2x plus 180 minus 2y is equal to 360. So this gives us b minus 2x minus 2y is equal to 0. So that'll give us b equal to 2x plus 2y, which is equal to 2x plus y. And so because x plus y is actually the angle at the circumference and b is the angle at the center, we have proved that this theorem holds for every circle. So the next circle theorem is that the point at which a tangent to a circle meets a radius of the circle is a right angle. So as you can see, we have a circle C and two tangents to it, which are the lines AD and AB. And I have also drawn two radii of the circle, which are the line CD and CB. So as you can see, the tangent AD meets the line CD at the point D, and since AD is a tangent to the circle and CD is a radius, the angle CDA must be a right angle. So this is a right angle. Also, the line AB is a tangent to the circle, and the radius CB meets the line AB at point B, and so the angle CBA must also be a right angle. Okay, so the next circle theorem is that two tangents that originate from the same point are equal in length. And so in essence, what we're going to show is that the line AD is equal in length to the line AB. And we're going to do this using congruent triangles. So the first step is to join the point C to the point A. Once we have done that, we are now going to prove that the triangle CDA is congruent to the triangle CBA. So firstly, we can note that angle CDA is equal to the angle CBA. Also, we can note that both triangles have the length CA in common. Finally, we can note that the length of CD and CB are equal, as they are both radii of the same circle. So CD is equal to CB. So with these three facts, we can now use the fact that if two triangles have a right angle, a hypotenuse of the same length, and another side in common, then they must be congruent. And so because angle CDA equals angle CBA, which equals 90 degrees, and the side CA is common to both triangles, which is the hypotenuse, and the length CD is equal to the length CB, as both are radii of the same circle, we can now deduce that the triangle CDA is in fact congruent to the triangle CBA, and so corresponding sides are of the same length, and so AD is equal to AB. Okay, so the next theorem that I'm going to show you is that the angle in a semicircle is always a right angle. If we draw a diameter of the circle, and then if we draw a triangle using this diameter as one of its sides inscribed in the circle, so if we say a shape is inscribed in a circle, it just means that all of the shape's vertices lie in the bigger shape. So if I'm saying that a triangle is inscribed in a circle, it means that all of the vertices of the triangle lie on the circumference of the circle. So for example, I could draw it like this. Okay, so we have a triangle where all vertices are on the circumference of the circle, and one of the sides is the diameter of the circle. And so what this theorem states is this angle here is a right angle. So like before, I'm just going to quickly prove this. If I join the center to the right angle here, as like that, what we can then see is that we end up with two isosceles triangles, and what we can then do is start labeling the angles in the triangle. So if I call this angle A, then this angle here will also be A, and if we call this angle here B, then this angle will also be B. And then because angles in a triangle add up to 180 degrees, then we get A plus B plus A plus B is equal to 180. And so 2a plus b is equal to 180. And so a plus b is equal to 90. And a plus b is this angle here. Therefore, the angle in a semicircle is always a right angle. Okay, so the last theorem that I would like to talk about is that opposite angles in a cyclic quadrilateral add up to 180. So a cyclic quadrilateral is just a quadrilateral that is inscribed in a circle as seen on your screen. Okay, so what this theorem states is that if we take any angle, such as this one here, and let's call it A. If we then take the angle opposite to that one, so this one here, and call it B, then what this theorem tells us is that A plus B is equal to 180 degrees. So how can we prove this? Well, it actually involves using the first theorem that I talked about. So what we're going to do is join each of the remaining two vertices to the center of the circle. So, for example, so here and here. The first theorem tells us that the angle at the center is twice the angle at the circumference. So what we can then say is that this angle here is 2a. And we'll get that this angle here is 2b. Then because angles around the point add up to 360 degrees, we can say that 2b plus 2a is equal to 360 degrees. And so dividing both sides by 2 gives a plus b equals 180 degrees as required. Okay, so the first question is, two circles with radii 1 centimeters and 4 centimeters touch. The point P is on the smaller circle, Q is on the larger circle, and PQ is a tangent to both circles. What is the length of PQ? Okay, so the first thing that we're going to do is what I like to do with all questions involving circles, and that is to mark down the centers of both circles. So the center of Q is going to be about here, and the center of P is about here. And that what we're going to do is we're going to join the centers of both circles to other important points. And so what I mean by important points are points such as tangents and like centers of other circles and just things like that. So okay, so now we've done that, we can continue with the question. So I'm just going to quickly label the centers of the circle. I'll just call them M and N for now. And what we can then do is we can start labeling these lengths. So we know that PM is 1 centimeter, so has a length of 1. QN has a length of 4. And MN is the sum of the radii of these two circles. So the length MN is 4 plus 1, which is 5. Okay, so what we are then going to do is, because this is from the UKMT maths challenges, a lot of the times it's a good idea to try and create right angles and then try to apply Pythagoras' theorem to try and find missing lengths. So what we're going to do is we're actually going to draw the perpendicular from the vertex PM to the line QN. So this angle here is a right angle, and so is this one. And what we're going to do is we're going to label this point here where the line meets QN. We're going to call it T. What we can then do is, we know that the length of QN is 4, and so that means that the length of QT is 1, because it'll be the same as the length of PM, so this is 1. And the length of TN will be 4 minus 1, which is 3. Okay, so now we have a right angle triangle, TNM. So by Pythagoras' theorem, the length TM will be equal to, so TM will be equal to the square root of 5 squared minus 3 squared, which is equal to 4. So the length TM is equal to 4. We also have a rectangle made by the vertices P, Q, M, T, as the angle PMT is also a right angle, as is the angle MPQ, as it's where a radius meets a tangent, and also by the same logic TQN is. And so therefore the length PQ is equal to MT, which equals 4. And so the answer to the question is E. Okay, so the second question. PQR are points on the circumference of a circle of radius 4. Angle PQR is equal to 45. What is the length of chord PR? Okay, so as before, we are going to mark the center of the circle, so here, and we'll call that point O. So, like before, we can then start joining the center to relevant points on the circumference of the circle. And so this time, we're actually going to join it to the points P and R. And so now what we can do is start applying the first theorem that we talked about, which is that the angle at the center is twice the angle at the circumference. So the angle at the circumference is 45 degrees, and so the angle at the center, which is the angle POR, must be 90 degrees, because it's 45 times 2. So this angle here is a right angle. And what we can then do is that we can start using Pythagoras' theorem again, because we know that PO and OR are both the radii of the circle, and so they both have length 4 here. And so we know that PR is equal to the square root of 4 squared plus 4 squared, which is equal to the square root of 32, which is then equal to 4 root 2. And so the answer to this question is C. Okay, so the third question is, PQRS is a quadrilateral inscribed in a circle of which PR is a diameter. The lengths PQ, QR, and RS are 60, 25, and 52 respectively. What is the length of SP? Okay, so I'm just going to quickly mark on these lengths. 25, 52. And we're also told that PR is a diameter of the circle. There to there. And so now what we can then do is we can deduce some of the angles in this quadrilateral. So because PR is a diameter, we can use a theorem that tells us that the angle in a semicircle is always 90 degrees. And this tells us that the angle PQR is 90 degrees. And so what we can then do is we can start using Pythagoras' theorem. So we'll end up with PR is equal to the square root of 60 squared plus 25 squared, which comes out as 65. So the length PR is 65. And similarly, by the same logic, we can deduce the angle PSR because the angle in a semicircle is 90 degrees, we can say that the angle PSR is 90 degrees. We know the hypotenuse of the triangle is 65. So we can use Pythagoras' theorem again to start working out the length of PS. So SP is equal to the square root of 65 squared minus 52 squared, which is equal to, using my calculator, 39. So the final answer is 39, and this corresponds to E. Okay, the fourth question is, the diagram shows 4 touching circles, each of which also touches the sides of an equilateral triangle with sides of length 3. What is the area of the shaded region? Okay, so the first thing that you should notice is that this shape here, so this triangle, has 3 lines of symmetry that correspond with the lines of symmetry of an equilateral triangle. Okay, so what we're now going to do is we are going to call the radius of one of the small circles R, and we're going to call the radius of the big circle from here to there, we're going to call that big R. Okay, so now what we're going to do is we're actually only going to consider a third of the shape. So this big circle here and one little circle. And so I'm just going to consider this circle here for now. And so like before, we are going to draw join the centers of this big circle here and the center of this little circle here to important points on the circle, which in this case happen to be the tangents to each circle. So one there, and one down, and then here and here, and then also one down there. And I am going to join this center here to the one vertex of the equilateral triangle. So now, just for ease, I'm going to start labeling some of the points. So I'm going to call this point here A, this point here B, this point here C, this point here D, and this point here P. Okay, so we can now start labeling some of these angles here. So we know that this point here is where a radii of a circle meets a tangent to the circle, and so the angle PCA is equal to 90 degrees. And by similar logic, the angle PDB is equal to 90 degrees also. And what we can now do is say that the triangles PDB and PAC are similar. And so how do we know that? Well, we can see that both of these triangles contain the exact same angles. So they both have a right angle, they both share the angle BPD, and so by the same logic, and then because the angles in a triangle add up to 180 degrees, the third angle in both triangles must also be the same. So therefore, we can show that PDB and PCA are similar. So what this means is that the ratio of their sides are the same. So if this is R, this length here will actually also be R. This is little r, and this is also little r. And then also, because we've drawn the line of symmetry of the triangle, this angle here of 60 degrees of the equilateral triangle must have been split in half when we drew this line here. And so actually let's just label this, let's label this T. So the line PT must bisect this angle here, and so the angle BPD must be equal to 60 divided by 2, which is 30. Okay, so what we can now do is start, as I said before, using the fact that those two triangles are similar. And so because we have a right angle triangle PUPD, we can start using trigonometry, and so we can say that tan 30 is equal to BD over PD, which is equal to R over PD, and so PD is equal to R divided by tan 30, and so the side PD will come out as R root 3. So as I said before, because we know that the triangles PDB and PCA are similar, we can start then using the fact that the ratio of their sides are the same to create some equations. So we can say that, well, firstly, we know that the side PC is equal to 3 over 2, as it's half of a side of an equilateral triangle. So we can say that 3 over 2 divided by R root 3 is equal to R divided by R. Then this comes out as 3 over 2R root 3 is equal to R over R. We can then times both sides by R, which will get rid of this R and this R. And then what we've done there is we found that R is equal to 3 over 2 root 3. If we then times both sides by 2 root 3, this will give us 6. R is equal to 6 root 3 over 12, which is equal to root 3 divided by 2. So I'm just now going to quickly rub out this board so we have more space. So I'm just going to actually write here that R is equal to root 3 over 2. Okay, so we just worked out that R is equal to root 3 over 2. And so now, to finish up the question, we need to start trying to work out the length of little r. So one way you can do this is that you can start using trigonometry again, but instead we'll construct an equation that involves using the length of PT. So we can work out the length of PT by Pythagoras' theorem. So PT is equal to the square root of 3 squared minus 3 over 2 squared. As remember that PT, that we can have a triangle if I call this Q and this R. You can have the triangle PTQ is equal to the length of the equilateral triangle, which is 3, and half the length of the equilateral triangle, which is 3. And then because of that, we can start using Pythagoras' theorem with these two sides to find out the length PT. And so we'll get PT is equal to 3 root 3 over 2. Also, we can work out the length of PB in terms of R. So using trigonometry again, we will get that sine 30 is equal to BD over PB, where BD is the opposite of the angle BPD in the triangle PDB, and PB is obviously the hypotenuse. So then that's equal to R over PB, and so PB is equal to R over sine 30. which is equal to 2r. So now we can see that the length PT is made up of the length PB, the length BR, and the length RT. So we can say that PT, which is 3 root 3 over 2, is equal to the length PB, so 2r, plus the length BR, which is r plus little r, plus again the radius of the big circle, which is r. So what we then get is that 3 root 3 over 2 is equal to 3 little r plus 2 big R. And so we know that 2 big R is equal, we know that big R is equal to root 3 over 2. So 2 big R is equal to root 3. So we'll get that 3 root 3 over 2 is equal to 3 little r plus root 3. This then gives us that 3r is equal to 3 root 3 over 2 minus 2 root 3 over 2. And so that gives us that 3r is equal to root 3 over 2. And so r is equal to root 3 over 6. And so let's just make sure that little r is smaller than big R. And yes, it is. So this all makes sense. And we can then start using these sides to these radii to work out the area of the shaded region. So again, I'm just going to quickly erase the board. Okay, so we know that little r is equal to root 3 over 6. And so what we can now do is work out the shaded region. So the shaded region will be equal to pi times big R squared. So root 3 over 2 squared plus 3 pi times little r squared, so root 3 over 6 squared. And if you work this out, that will come to 3 pi divided by 4 plus pi over 4, which is obviously equal to 4 pi over 4, which is then equal to pi. So the answer to this question is B. So this is quite a long question, and you'd expect it to be right at the end of a UKMT paper, if not the last question. Okay, so the last question is, the diagram shows a pattern found on a floor tile in the cathedral in Spoleto, Umbria. A circle of radius 1 surrounds 4 quarter circles, also of radius 1, which enclose a square. The pattern has 4 axes of symmetry. What is the side length of the square? So, as you can see, I've actually added some lines to the diagram, and I'm just going to quickly explain them. So we have 4 arcs here. So what I've done is I've marked the radius of each arc, and I've connected the center of each arc to the respective endpoints of each arc. So for example, for this arc here, I've drawn the center as P and joined P to this side here and this side here. And I've done that for every arc. And what it actually gives you is a square. So PQRS is a square. And the side length of the square is 2, as it's made up of 2 radii of length 1. What I then did is I marked the center of the circle, which is C, and then I joined P to C and Q to C. So we know this length here is 2. And so what we can then do is that we're going to mark this point here where the square meets one of the arcs. So this point here will be T, and we call the same point here U. So what we can now do is we can work out the length of PC using Pythagoras' theorem. So we know that the length PC is equal to CQ because of the symmetry of the shape, and so we can say that 2PC squared is equal to 4, and therefore PC is equal to root 2. And because we know that the length PT is equal to 1, we know that the length TC is equal to root 2 minus 1. We also know that because of the symmetry of the figure, the length CU is also root 2 minus 1. So CU is equal to root 2 minus 1. And now what we can do is that we can use Pythagoras' theorem again, because obviously the triangle CTU is right angled, and the length CT and CU are just in fact half of the diagonals of the square. So we can say that UT, which is one side of the square, so UT squared is equal to TC squared plus CU squared. And now because TC and CU are equal, we can rewrite this as UT squared is equal to 2TC squared. And if we then square root both sides, we'll get UT is equal to root 2 times TC, which is equal to root 2 times root 2 minus 1, which is equal to 2 minus root 2. And this corresponds to B.